Hello, welcome to Computational Statistics, getting started with classification using MATLAB. My name is Richard Willey, and I'm Product Manager for the Statistics products here at the MathWorks. Before I begin, I'd like to take care of a few logistical issues. If you have any technical difficulties during the presentation, please use the chat tab to correspond with the webinar host. If you have questions about the content, please post them to the Q&A tab, and we'll do our best to answer them all at the end of the presentation. Here's the agenda that we'll be using today. I'm going to start out by giving a brief overview of what classification is and why you'd want to use it. Next, I'm going to present a standard workflow that often gets used when one is working on a classification problem. After this, we'll move into MATLAB and apply the techniques that we've just discussed to a real-world problem. I'll conclude the presentation by showing you where you can get additional information, as well as answer questions posted during the presentation. Okay, let's get started. At the most basic level, you can think of classification as predictive modeling. We're trying to predict some dependent variable y as a function of a set of independent variables. Intuitively, this is very similar to regression and curve fitting. What distinguishes regression from classification is the nature of the model that we're producing. Regression models y as a continuous variable, while classification treats y as a variable that might belong to one of a few discrete classes. In this example, I have a classification system with 4 discrete classes. An animal in my backyard could either be a bird, a dog, a fish, or a snake. Here are a few examples that show how classification algorithms get used in a variety of industries. Classification algorithms are used extensively in financial services. Automatically assigning bond ratings is a very well-known example. Here I'm showing a simple application that was developed using MATLAB that predicts credit ratings based on information from a corporate balance sheet. Notice that this is a classification problem. The credit rating falls into a small number of discrete classes, from high-rated AAA borrowers down to CCC. Biopharm is another industry where we see heavy use of classification algorithms. This example shows a classification algorithm that was designed to identify tumor type. The tumors belong to one of 4 discrete classes. The classification algorithm automatically predicts tumor type based on the DNA profile contained within the cancerous cells. Classification algorithms are often used to post-process video images, acoustic signals, or even a combination of both. The examples here are almost endless. Optical quality control systems apply classification algorithms to pictures of finished goods. Handwriting recognition systems use classification algorithms to read print. I have an application on my cell phone that can listen to a bird song and tell me what type of bird is singing based on an acoustic signal. Now please note, here I'm going and describing classification as a post-processing step. All of these examples start with a feature extraction phase in which critical information from a signal is transformed into a format, a matrix, that the classification algorithm can operate on. At this point in time, I'd like to start talking about applied classification. I'm going to start by identifying some challenges that users often encounter while working with classification algorithms, after which I'll describe a recommended workflow. One significant challenge is the level of technical expertise required to apply some of these methods. Machine learning techniques like classification are often new to engineers. Some of the techniques involve specialized knowledge. For example, deciding what classification algorithm to use can be challenging. Another problem that users often encounter is black box solutions. As we're going to see, creating an accurate classifier can be an open-ended process. You often need to customize your analysis based on unique characteristics of your data. Sometimes you even need to develop your own custom analysis routines. The time required to conduct your analysis is another important challenge that users face. Designing a classifier often requires a lot of different steps and some custom coding. It's important to have a working environment that allows you to quickly prototype your analysis and quickly run your code. At this point in time, I'd like to describe a typical workflow that one might use when working on a classification problem. I'm going to provide a basic overview of each of these steps and also discuss some of the capabilities that MATLAB provides for each stage of this process. As soon as we're done here, we'll jump into Statistics Toolbox and apply the same workflow to a real problem. The first step in your classification workflow is determining what classification algorithm you should be using. Statistics Toolbox provides a wide variety of classification algorithms, including linear and quadratic discriminant analysis, logistic regression, classification trees, naive Bayes classifiers, and bag decision trees. If we look a little bit further afield, Bioinformatics Toolbox offers support vector machines, and Neural Network Toolbox also provides some powerful classification capabilities. Determining which classification algorithm to use is often the trickiest part of your entire problem. At the core, choosing a classification algorithm is a balancing act. There is an inherent trade-off between the complexity of the algorithm that you're using and how restrictive your assumptions are about the data that you're working with. At one extreme, you have some very simple, easy to understand algorithms like discriminant analysis. Unfortunately, discriminant analysis relies on some very restrictive assumptions. If your data doesn't match these assumptions, the algorithm probably won't produce accurate results. At the other extreme, you have complex algorithms like bag decision trees, support vector machines, and the like. These models will operate on a wide variety of different data sets. Unfortunately, the resulting models can be extremely complex. Here are a couple of rules of thumb to help get you started on algorithm selection. First, simpler is usually better. Simple models are easy to interpret. They're also easy to explain to other people. This can actually be a critical requirement. Consider that credit rating example that we discussed a moment ago. Banks are often legally required to be able to explain how they make their lending decisions. Banks need to be able to explain, in simple English, how their algorithm is working. Simply stating that this black box algorithm is denying you credit is insufficient. Simple models can also have significant advantages in terms of execution speed and memory requirements. At the core, you are essentially trying to identify the simplest model that is consistent with the data set that you're working with. As such, you're going to need to examine your data and determine which, if any, of the underlying assumptions for the different models are being violated. This is an exploratory data analysis task, and it's an example where MATLAB's visualization capabilities and advanced analytics really shine. Once we've selected our classification algorithm, the next step is to train our classifier. Classification is a supervised learning technique. Classification starts with a known data set that contains a reliable mapping between features and classes. When we train our classification algorithm, we develop a set of rules that tries to replicate the same judgment. Once we've trained our classifier, we can then use it to make predictions about a brand new data set that only contains features. In most cases, you'll want to separate your data into a test set and a training set. You'll train your classifier on the training set and then test its accuracy on the data that you reserved. As you might guess, the next step we're going to look at is measuring the accuracy of our classifier. Statistics Toolbox provides a wide variety of different functions that you can use to measure the accuracy of a classifier. The confusion matrix is a simple visualization tool that you can use to plot the predicted class versus the true class. Anything that is located on diagonal is classified correctly. Anything that is off diagonal is misclassified. If you prefer a more visual approach, you can plot the same information using a parallel coordinates chart, or alternatively, a ROC curve. The ROC curve, or ROC curve, is used to explore the sensitivity of the classifier. It shows the trade-off between the true positive rate and the false positive rate. The parallel coordinates chart provides a simple graphical summary of the information contained in the confusion matrix. Each observation in the test set is represented by a curve. The color of the curve shows the true class, while the peak in the curve shows the prediction. In this example, the blue line represents EW tumors. As you can see, each of the blue lines has a peak in the EW bin, indicating that this classifier is doing a very good job predicting this type of tumor. Of course, if you prefer, you can use MATLAB scripting capabilities to develop your own custom analytic routines or your own custom metric. In some cases, you might not be able to produce a sufficiently accurate classifier. In this case, you might have to go and loop back to the algorithm selection process and try a more powerful method. Our next step is to try to simplify our classification model. More explicitly, we want to see whether we can identify a minimal set of features that is able to achieve the same accuracy as our complete model. At this point in time in the talk, people normally ask, why is simplicity important? Why would I care about anything other than accuracy? And here's a quick answer. Complicated models often run into trouble with overfitting. You produce a model that does a great job describing your training set, but isn't nearly as accurate as describing the test set. In some cases, simplifying your model can even improve predictive accuracy. Next, reducing the number of features reduces the size of the resulting model. If you need to deploy your model into hardware, you're often constrained with respect to size. Finally, parsimony, or simplicity, is considered valuable in its own right. Think of Occam's razor. You should typically prefer the simpler solution or simpler explanation. MATLAB provides a number of different techniques that can be used to address this problem. The two most important techniques are what's known as cross-validation and out-of-bag variable importance. Once we've simplified our classification model, we're ready to start doing something useful with it. We can now use our trained classifier to start making predictions about new data sets. In many cases, the trained classifier will get wrapped into a graphical user interface and deployed to other users. Other times, a trained classifier will get embedded into a production system, such as a sensor network, a trading system, or in my favorite example, you often see naive Bayes classifiers used for spam filters. So, at this point in time, let's go, jump into MATLAB, and see how we can put all this theory into practice. Our demo shows how to train a classifier that predicts the quality of wine based on its chemical composition. White wine is an Excel file that contains information about roughly 5,000 different Portuguese white wines. Each row in the spreadsheet represents a different wine. Each of the wines was tasted by a panel of experts. The experts graded the quality of the wine on a scale of 1 to 10. Quality is our class label, and our classifier is going to try to predict this value. Each of the wines was also chemically analyzed. As you can see, we have information about the alcohol content, the acidity, and the residual sugar. In total, we have 11 different chemical markers, and these are the 11 different features that we're working with. Our goal is to design a classification algorithm that can replicate the judgment of the expert panel. I'm going to start by getting some preliminaries out of the way. I'm going to clean up our workspace, import the data into MATLAB as a dataset array. Next, I'll define two variables, y that contains the class information, and x that contains my features. Finally, I'll set the seed for the random number generators so we can precisely replicate this analysis at a later point in time. As a first step, I need to decide which of the various classification algorithms I want to use. I'm going to start with some exploratory data analysis to try and understand whether this particular dataset is consistent with some of our simpler classification algorithms. As a first step, we're going to see whether or not our features are normally distributed. This assumption of normalcy is central to many of the simpler classifiers like linear discriminant analysis. I'm already pretty sure that my features aren't normally distributed. Many of my features like alcohol content and density can't take a negative value, which means that they don't follow a normal distribution. Even so, I'm going to use the norm plot function to see whether this actually has a significant impact on the dataset. If my data is normally distributed, then the blue crosses, which describe individual data points, should follow the red line. NormPlot shows me that a number of these variables skew sharply away from a normal distribution. I'm going to look at the plot for residual sugar in isolation so you can see this in a little bit more detail. As you can see, the tails clearly deviate sharply from what we'd expect to see with a normal distribution. Next, I'd like to see whether or not my features are strongly correlated with one another. Independence between features is an underlying assumption of a naive Bayes classifier. This analysis will give me some idea whether the naive Bayes classifier is a good choice. Based on theory, I know that some of these features should be correlated with one another. For example, the density of the wine changes as we convert sugar into alcohol, so I'd expect to see a strong correlation between residual sugar and density. I'm going to calculate correlation coefficients between the different variables, and then plot this as a heat map so we can easily see what's going on. The heat map shows that a number of these variables do exhibit strong correlation. As I expected, there's a strong positive correlation between density and residual sugar, and a strong negative correlation between density and alcohol content. It's also interesting to note that there's a strong positive correlation between the alcohol content and the quality of the wine. The judges apparently like their wines very strong. Keep this data point in mind when we hit the feature selection step. Even though many of these features exhibit correlation, I'm still going to start with the naive Bayes classifier. It's unclear whether or not these correlated features will all survive the feature selection process, so it's quite possible that the naive Bayes classifier will still work well. Also, the assumption that a naive Bayes classifier requires independent features is a nice piece of theory. In practice, these classifiers often work pretty well, even if there's correlated features. Before I train my classifier, I want to separate the data into a test set and a training set. The CV partition in MATLAB is the easiest way to do so. I'm going to create an object C that contains all of the information about the test set and the training set. I create C using the CV partition function. The holdout option says we're creating a test set and a training set. And the parameter point2 tells CV partition to reserve 20% of the data points for my test set. It's worth noting that Crossval will automatically design the test set and the training set so that different wine classes are equally distributed across the two sets. Believe me when I say that functions like this will save you a lot of time and effort. I'm going to create the actual training sets by indexing into C, extracting out a logical vector, and applying this to the x and y variables. Believe it or not, this next little line of code is all that I need to do to train my naive Bayes classifier. I'm telling naive Bayes to fit a model that predicts y train as a function of x train. Now that I've trained my classifier, I'm going to use the reserved test sets to check the accuracy of my model. I'm going to start by generating a confusion matrix. I'm also going to create a simple summary statistic that tells me what percentage of the test set ended up off the diagonal. As you can see, only about 50% of the test set was classified accurately. As a next step, I'm going to see whether simplifying my model is able to improve the accuracy. There are a couple different reasons why simplifying the model might improve performance. First, as we discussed earlier, complex models often run into trouble because they overfit the data. The algorithms develop very accurate rules that describe this one specific training set. However, the results can't easily be generalized to other data sets. Also, I have some worries about the correlation between the variables. If we can simplify our model and only include variables that are uncorrelated with one another, the accuracy of the naive Bayes classifier might improve. First, I'm going to use CV partition once again. This time I'm going to use tenfold cross-validation rather than a simple test set training set combination. Notice once again how easy it is to apply cross-validation. Next, I'm going to use a technique called forward feature selection to simplify my model. Forward feature selection is pretty simple to understand. We start with a model that has no features included. We then create 11 models, each of which contains one of our 11 features, and we determine which one of these models is the most accurate. It looks like this first step is finished running. From the looks of things, forward feature selection has identified feature 11, the alcohol content, as the most important feature. Intuitively, this should make a lot of sense. If you think back to the correlation coefficient, our heat map showed a very strong correlation between alcohol content and quality. Next, the algorithm will test each of the remaining 10 features. We know that our model should include the feature with the greatest predictive power. We test how much more accurate the model becomes if we go and add a second feature. Once we determine the second most powerful feature, we then use the same process to test feature number 3. At each stage in this process, the algorithm will determine whether adding an additional feature generates a statistically significant improvement in the accuracy of the classifier. Forward feature selection will automatically terminate once it can't make any additional improvements to the model. Forward feature selection is finished running. It looks like forward feature selection is recommending a model that is based on a total of 4 features, numbers 1, 2, 6, and 11, which are fixed acidity, volatile acidity, free sulfur dioxide, and of course our old friend alcohol content. In addition, the act of simplifying the model has actually resulted in significant improvements in the accuracy. Earlier, our misclassification rate was a little over 50%. Simplifying the model has reduced the misclassification rate to about 46.5%. This is definitely a noticeable improvement in accuracy. However, I'd like to see whether another, more powerful classification algorithm might be able to improve on the results of the naive Bayes classifier. At this point in time, I'm going to haul out the heavy artillery and train a bag decision tree. Bag decision trees are a powerful algorithm which can often produce very accurate results. However, they're not very transparent. It's hard to understand just what the algorithm is up to or how it's making its decisions. In addition to accuracy, bag decision trees have a couple significant advantages compared to other classifiers. The treebagger algorithm has built-in support for cross-validation. It also has specialized functions that you can use to measure feature importance. When we are working with the naive Bayes classifier, we had to partition the dataset into a test set and a training set. Here, working with treebagger, I'm able to pass the raw x and y variables directly into the algorithm. When I executed the last cell, I instructed treebagger to provide a summary statistic called the out-of-bag error. This statistic is equivalent to the misclassification rate that we calculated with the naive Bayes classifier. Now that treebagger is finished running, we can see that this algorithm was able to construct a much more accurate classifier than naive Bayes. If you recall, the misclassification rate for the naive Bayes classifier was about 46.5%. With treebagger, this figure has dropped to 28.7. Even though bag decision trees provide equivalent functionality to cross-validation, it's still good practice to use a test set and training set if you have enough data. Here, I'm rerunning my model, this time with a validation set, just to confirm that nothing strange is going on. Treebagger is finished its second run. As you can see, the misclassification rate that we extracted from the confusion matrix is almost identical to the out-of-bag error. One important point to know about treebagger. Bagging stands for bootstrap aggregation. I'm not going to go into all the technical details about bootstraps. For now, the important thing for you to know is that bootstraps involve random sampling. When you're working with bag decision trees, you're going to see a small amount of variance between runs. This is perfectly normal and to be expected. The next thing that I want to show you is how treebagger does feature selection. One of the statistics that you can pull out of the bag decision tree object is the out-of-bag var delta error. I'm going to create a bar chart that displays this value for each of the 11 features that we're working with. The height of the bar indicates the relative importance of each feature. As you can see, this feature selection technique also identified the alcohol content and the volatile acidity as the two most important features for our classifier. Feature 6, free SO2, was also tagged as being very important. In many cases, you'll be able to look at this chart and immediately identify a small number of features that clearly provide most of the explanatory power. In this example, I'm not quite sure which of the features to include, so I'm going to run my sequential feature selection algorithm one more time and see what it recommends. It looks as if the sequential feature selection algorithm is recommending a model that includes 9 of the 11 features. And as you can see, this model is able to accurately classify the wine type roughly 70% of the time. The last thing that I want to show you during our demo is how to create an ROC curve. ROC stands for Receiver Operator Characteristic Curve. They are extensively used in the field of signal detection and actually date back to early radar systems. Statistics Toolbox allows you to create ROC curves using the perf curve function. ROC curves are used to describe the sensitivity of a binary classifier. The shape of the curve shows the trade-off between a false positive and a false negative, equivalently the trade-off between type 1 and type 2 errors. As we move upwards and to the right along this curve, the chance that we detect a true positive increases. However, we also increase the percentage chance that we'll trigger a false positive. Area under this curve, or the AUC, is used as a scalar that describes the overall accuracy of the ROC curve. ROC curves are typically used when you want to tune your classifier and adjust the sensitivity with which the algorithm detects different classes. Hypothetically, you might want to make it very unlikely that a high-quality wine was rated with a low quality. Of course, your trade-off is that it becomes much more likely that a low-quality wine would get rated as high quality. Treebagger supports this capability using a weight option. When you load your dataset, you can assign weights to individual data points and instruct the algorithm to be particularly careful to classify these points correctly. At this point in the demo, we're done training our algorithm. We've produced a new trained classifier which is stored as an object. We can now use this classifier to start making predictions about brand new data that only contain features but no information about classes. We also have lots of information about the accuracy of our classifier. How confident can we be in the results that this algorithm produces? So let's move back into PowerPoint and start wrapping things up. We started this morning's discussion looking at a slide that showed a simplified workflow that people often use when they're working on a classification problem. I'd like to quickly work through this model once again and review the different techniques that we used during the demo. I'm also going to point you at some other capabilities in Statistics Toolbox that you'll want to be aware of. As a first step, we decided which classification algorithm we wanted to use. This was an exploratory data analysis problem where we used visualization techniques to understand our data. If we wanted to be a bit more formal about things, we could have used hypothesis tests, and Statistics Toolbox supports a wide variety of hypothesis testing. Our next step was to train our classification algorithms. We trained 2 different classifiers. We started with naive Bayes, and then we moved on to bag decision trees. As I mentioned earlier, Statistics Toolbox supports a wide number of different classification algorithms. You can use the classify command to access discriminant analysis. Class reg tree lets you work with a single decision tree. and the MNR fit function is used for logistic regression. Next, we measured the accuracy of our trained classifier. The primary functions that we used were CV partition to create test sets and training sets, the confusion matrix, OOB error, and perf curve. However, there are a wide number of other techniques that can be used to understand the accuracy of a classifier. Finally, we went and simplified our model. The most important function that we used was sequential FS. However, as we discussed, Treebagger also provides built-in support for measuring feature importance. We also discussed a number of different challenges that classification can present for an engineer. I hope that I've been able to convince you that MATLAB and Statistics Toolbox successfully address each of these challenges. Statistics Toolbox provides a simple and intuitive set of functions that you can use to solve classification problems. We were able to do a lot of very interesting work using a small number of simple functions. In addition to this, the MathWorks provides a lot of great example code, demos, and documentation that you can use to learn more about the techniques that we looked at today. It's also important to note that Statistics Toolbox and MATLAB provide you with an extensible programming environment. If you need to design your own custom analysis functions or visualization techniques, MATLAB gives you all the tools that you need to do so. If you want to inspect the code for our algorithms, see how they are implemented, and maybe even customize or extend them, MATLAB lets you do so. If you want to deploy a trained classifier into a production system or embed this into an Excel spreadsheet, MATLAB lets you do so. Last but not least, MATLAB lets you solve all of these problems quickly. MATLAB provides a great environment for rapid prototyping for new algorithms and new analysis techniques. The power and simplicity of our language lets you get work done quickly. It's also important to note that all of the core functions that we were working with today support parallel computing. If your bag decision tree isn't training quickly enough, get a copy of Parallel Computing Toolbox and throw the problem onto a cluster. The last thing that I want to do before we move into the question and answer section is to point you at some resources on the MathWorks website where you can find more information. First, all of our product documentation is available on the Statistics Toolbox homepage. Our developers have put together some really great demos that will show you a lot of very powerful techniques. I'd especially like to recommend the Treebagger documentation in the user guide. This contains 3 great applied examples that show you how to put the algorithm through its paces. We also have a number of other webinars that focus on classification problems. There are 3 webinars in particular that you should take a look at. Applied multivariate classification in the life sciences focuses on the tumor prediction example that we discussed earlier. This webinar is a great applied example for scientists. It also provides a lot more depth and detail about the Treebagger algorithm. The Credit Risk Modeling with MATLAB webinar provides an in-depth treatment of the bond rating example that I showed you earlier. This webinar should be interesting to anyone from the financial services industry. However, it also shows you how to wrap a trained classifier in a GUI and deploy these capabilities to non-MATLAB users. So if you're particularly interested in deployment, this is a great place to go. We also have a great webinar that uses a combination of bag decision trees and neural networks to forecast load on the energy grid. This should be loaded to MATLAB Central within a couple days. As always, all of the example code that we used in these webinars can be downloaded from MATLAB Central. This is another great way that you can start working with these functions immediately and get some practical experience. Speaking of which, all the demo code for today's webinar should be available within a couple weeks. Thanks all for listening. We've gotten a lot of really good questions, and I'll do my best to get all of these answered before the end of today's presentation. Thank you.